Okay, now we're ready to move on to section 4 of chapter 30, which is all about Lenz's law. I recommend you have a read through the textbook, Knight, page 845 to 847. If you don't have Knight, you can read any book. Stuff's been the same for hundreds of years. Here's where we really get to the heart of the Faraday effect. So if we move a magnet through a conducting loop, we get a current flow. And the direction of the current flow depends on the movement of the magnet. If you had looked at one of the videos from last time, you saw him move the magnet in and out, and the galvanometer switched one way and then the other way. I would suggest that you try that yourself a little bit. If you Google Faraday's law, you'll open up a simulation which shows, and you can just kind of experiment a little bit with the idea of changing the magnetic flux. You can change the orientation of the magnet, you can change which way it's moving, you can put in a couple of loops, and as you're doing it, you can watch what happens to the potential or the voltage. Then if you remember that V equals IR, whatever happens to the voltage is also happening to the current. So you can really experiment a bit with that FET simulation, and it gives you an idea of what's going on. And then just to make it a little bit more fun, the light bulb gets brighter and dimmer. So the direction of the induced current is summarized by Lenz's law, and this is really kind of neat. It says that there is an induced current in a closed conducting loop if and only if the magnetic flux through the loop is changing. The direction of the induced current is such that the induced magnetic field opposes the change in flux, and that change part is the important part. What it means, and I find this just the coolest thing of all physics, this is what got me to do a physics degree and then a master's and then a PhD, is that nature doesn't like any change in a magnetic field. Anytime we change an existing magnetic field, nature will induce a new magnetic field to oppose that change. We'll always make a new field so that it gets back to normal. I think that's really kind of amazing. So that's pretty nifty. That's Lenz's law. So it's a qualitative description of Faraday's law. We're going to do some examples of Lenz's law next. So the next couple of slides will be examples of Lenz's law. Then we'll move on to the quantitative description of Faraday's effect with Faraday's law. That'll give us the numbers to go with the directions. Okay, so we'll do some examples next.